In a previous video, we saw how the transformer architecture took over language modeling. This time, we'll see how it expanded into vision, where it became the backbone for tasks like image classification, image generation, and even video generation. At first, it wasn't obvious at all how to move from language to vision. Researchers had to answer two main questions. One, tokenization. How do you take something continuous like an image and turn it into a discrete sequence of tokens that resembles text? And second, conditioning. How do you get an image or a video generation model to listen to a text prompt, which is inherently such a different form of expression? We'll look at three architectural adaptations to the original transformer which answer these questions: the Vision Transformer, or ViT, the Diffusion Transformer, or DiT, and the Multimodal Diffusion Transformer, or MMDiT. My goal is to build them incrementally so that they feel less like a bag of tricks and more like inevitable design choices. But first, we'll start with a quick recap of the transformer architecture. The transformer was initially designed for machine translation, converting text from one language to another. Its origin story explains why the transformer has two main components, an encoder and a decoder. The encoder was meant to process the source text with bidirectional attention. For each input token, it outputs a contextual embedding, a real-valued vector that captures the token's meaning in the context of the entire sequence. The decoder uses this processed representation to generate the translation one token at a time, autoregressively. Its attention is causal. Each output token can only depend on the ones that came before and cannot peek into the future. While left-to-right processing is intuitive for language, since it mirrors how we read and process text, the same framing doesn't translate well to vision. As humans, we process images holistically, where every part can inform every other part. So bidirectional attention is a more natural choice. That's why most modern vision transformers only borrow the encoder component. Let's start with the simplest vision task, image classification. Given an image like this, the model needs to pick a label from a predetermined list that best describes it. Image classification was dominated by convolutional neural networks, or CNNs, for the longest time before transformers took over. In a previous video, we discussed how self-attention, the building block of transformers, is a much more general operation than convolution, the building block of CNNs. While convolution restricts a pixel's receptive field to a small neighborhood around it, self-attention allows it to look at the entire image. This generally enables scale and translates to model quality. But when applied naively to pixel level, self-attention becomes intractable. When every pixel attends to all the other pixels in the image, the computational complexity is quadratic. A small image of size 256 by 256 leads to billions of computations. And it gets much worse for high-resolution images. So using transformers in vision is predicated on reducing the number of elements that attend to each other. The Vision Transformer, or ViT, proposes a simple yet effective solution. Instead of operating on raw pixels, it splits the image into patches of 16 by 16 pixels each. This gives us a grid with 16 by 16 patches, all attending to each other. As the ViT authors put it, an image is worth 16 by 16 words. Operating on patches instead of pixels brings self-attention down from a few billion computations to about 65,000, much more tractable. Now that we split the image into 256 patches, which act like tokens, we're one step closer to the discrete sequence input that the transformer encoder expects. We just need some extra processing to flatten the 3D patches into 1D embeddings. Then a final linear layer with learned parameters changes the embedding size to match the hidden dimension of the transformer encoder, in this case 1024. And finally, since the transformer is position agnostic, we'll have to add position embeddings. For simplicity, in my diagrams, I'll hide the input processing pipeline behind the generic image embeddings box. With this input processing in place, the Vision Transformer can simply reuse the transformer encoder block to process the image. The ViT stacks multiple such blocks before producing a probability distribution over classes. To support image classification, the ViT borrows an idea from BERT, the well-known text classifier. It appends a special classification token named CLS to the input sequence. Because of the bidirectional attention in the encoder, the CLS gets to see all the image patches and becomes a sort of summary of the image. A final learned classification head converts the contextual output embedding of the CLS token into a probability distribution. And that is how the Vision Transformer performs image classification. The next natural milestone is image generation. The backbone of the initial image diffusion models was the UNet, primarily built from convolutions. But as the transformer gained popularity, the UNet was replaced by the Diffusion Transformer, or DiT. If you're not familiar with a diffusion paradigm, I suggest that you watch this previous video. Here, I will very briefly go through the fundamentals. You're probably familiar with the sequence of progressively noisier images. It starts with a clean image from the training corpus, which is gradually corrupted with Gaussian noise. Each time step is associated with a noise level, from 0 for the clean image all the way to 1 for maximum corruption. This is forward diffusion, a way of producing chains of training data. The model learns to walk this chain in reverse from pure noise to a meaningful image. In practice, running diffusion in raw pixel space is expensive. That's why modern diffusion models operate in a more compact latent space. With the help of an off-the-shelf external model called the VAE, or Variational Autoencoder, the raw image is compressed into a smaller three-dimensional tensor. Here, the spatial dimensions were reduced to 32 to save space, while the number of channels was increased from 3 to 4 to make room for richer features beyond just colors. So now we can encode the image with just 4,000 values. In this setup, diffusion happens entirely in latent space, both the forward and reverse paths. After reverse diffusion is complete, the final denoise latent is mapped back to pixel space using the decoder component from the same external off-the-shelf VAE model. During reverse diffusion, the trained model is invoked repeatedly, once per step, to partially clean an intermediate latent. One meaningful consequence is that the model doesn't have a holistic view of the entire chain and operates locally. That's why the time step itself needs to be an explicit input. Otherwise, the model wouldn't know how far in the denoising process it is. And of course, the final missing piece is a description of the desired content to generate. The original diffusion transformer was class conditional. It was trained on a fixed set of things like dogs and cats. So the user was only able to prompt it with one of these classes. We'll talk about fully fledged text prompting a bit later. So compared to the ViT, the diffusion transformer has a slightly different interface. To start with, the image input is no longer a raw image, but rather a compressed latent. The DiT borrows the patching idea we saw earlier in the ViT. The 3D latent is split into multiple 3D patches. In this case, there are 64 of them. These are then flattened into 1D patches. And now we're very close to what the transformer expects. We just need an additional learned linear layer to match the transformer's hidden dimension size, 1024. Again, I'll hide this complexity behind a generic image embeddings box. The ultimate output is a slightly less noisy latent, though some models might not predict it directly. Instead, they might predict an auxiliary quantity from which the latent is derived. For instance, the original DiT predicted how much noise there is in the input latent compared to the clean one. But the specific semantics of the output are not extremely relevant here. What matters is that the output has the same shape as the input. To achieve this, each output embedding is passed through a regression head. So each input patch eventually translates to an output patch with real values. And the final deterministic on-patch operation stitches them all together. To encode the time value, the DiT uses a fixed sinusoidal embedding, just like older diffusion models. And to encode the class, it uses a learned embedding, similar to token embeddings from an LLM vocabulary. Now that we sorted out the interface, the remaining question is, how does the model condition the image generation process on the time and class inputs? Well, the diffusion transformer paper looked at 4 different ways. They're shown in Figure 3 here, but we'll build them progressively. Today, models use one of these options or a combination of them, so it's worth understanding all of them. Option 1 treats time and class as extra tokens and simply concatenates them to the input patches. We'll call them conditioning tokens from now on. This technically works. Self-attention allows the conditioning tokens to influence all image tokens. But time and class are now competing with image tokens for attention bandwidth and might end up being ignored. This calls for a conditioning mechanism that gives time and class special treatment compared to the other tokens. Option 2 adds a new cross-attention block. Notice that this is not self-attention, it's cross-attention between image tokens, which are the queries, and conditioning tokens, which are the keys. In other words, each image patch attends to time and class, so the attention bandwidth is distributed only between the two labels. This setup removes the risk that conditioning tokens are ignored, but it's quite expensive computationally, the most expensive out of all 4 options. The additional attention adds 15% more gigaflops. Option 3 is more cost-effective and also a lot more interesting. It takes inspiration from an older paper called Film that was published back in 2017. At the time, they were working on visual reasoning, automatically answering questions about an image. Back then, convolutional neural networks were the dominating paradigm for image processing. CNNs internally operate on feature maps, sometimes called channels, which are transformations of an image focused on a particular aspect, be it high-level contours, fine-grained edges, or shapes. When answering questions, some feature maps are more relevant than others. For instance, when interested in the specific dog breed, it's helpful to look at the fine-grained details in the fur. When figuring out the rough position of the dog in the scene, the high-level contours are a less distracting signal. Film is a strategy to automatically amplify or suppress feature maps through a linear transformation. The scale gamma and shift beta are derived from the question embedding. Each feature map gets its own set of parameters, which are uniformly applied to every feature in the channel. Generally, this strategy is called feature modulation. The diffusion transformer borrows this idea in a creative way. Say, each patch translates to a flat embedding of size 1024 equal to the transformer's hidden dimension. In the DiT, the equivalent of a feature map is a slice of features that spans across all patches. So the first embedding dimension corresponds to feature map 1, the second embedding dimension corresponds to feature map 2, and so on. Basically, we'll end up with 1,024 feature maps, each requiring its own scale and shift parameters. For image generation, the conditioning signal is no longer a question, but rather the class and time inputs. And it's particularly intuitive why we would want to modulate features based on time. Early on at t equals 1, when the noise is so high, the model needs to focus on high-level structure. And as it gets closer to t equals 0, it could focus on finer details. The implementation is quite straightforward. The time and class embeddings are mixed together. One option is addition, followed by a multi-layer perceptron that produces the modulation parameters gamma and beta. The DiT authors are injecting modulation in 2 separate places, before the multi-head attention and the feed-forward block. Note that 1 and 2 are now indices of the group. In both of these groups, gamma and beta are vectors of 1024 values. This option is also called adaptive layer norm, or adaLN. That's because of its similarity to layer normalization, which also applies a scale gamma and a shift beta. The difference is these parameters are dynamically determined by the conditioning signal. And we've almost reconstructed the full diffusion transformer. Option 4 brings the final missing piece. It's something that is known to stabilize training, not just for the DiT, but also for older architectures like the ResNet or the diffusion unit. It has to do with the residual block, the one that combines the current activations with the ones from the previous layer. It was empirically observed that at the beginning of training, when the model weights are random, it's helpful to ignore upper layers and focus on the lower ones, effectively reducing the depth of the network in early stages. It's quite intuitive that this simplifies the learning problem. To achieve such an effect, it's common to add a simple scaling layer right before the residual block. This simply multiplies the current activation by a parameter alpha. If we initialize the parameters in such a way that alpha is 0 at the beginning of training, it will basically silence the current activation and implicitly reduce the depth of the network. The DiT defines alpha as a learned function that takes in the conditioning signal. So the time in class now influences the strength of the current activation. Conditioning on time is particularly helpful. Time is correlated with the amount of noise in the image and therefore with the difficulty of the task. It allows us to softly control the depth of the network based on how noisy the input image is. And that is the diffusion transformer. Its biggest limitation is that it's class conditional instead of allowing prompting through freeform text. Now, there is subsequent work that extended the DiT to text prompts. In particular, the Pixart-alpha model built on top of option 2, the one with cross-attention. They simply replaced the single class embedding with a sequence of token embeddings produced by an off-the-shelf language model named T5. While this technically works, it's a bit suboptimal. The text tokens are static. They're not influenced by the image. But in certain cases, like image editing tasks, this is very restrictive. A prompt like move the bat to the right means different things when referring to this image versus this image. The Multimodal Diffusion Transformer, or MMDiT, proposes a more principled approach. It treats images and text inputs symmetrically. They both get their own separate encoder parameters. The two modalities communicate through a joint attention mechanism. Basically, the image patches and text tokens are concatenated into one big flat sequence. The sequence attends to itself. Image patches get to see all the other image patches as well as the prompt tokens, and vice versa for the prompt in a symmetric way. This dual conditioning makes sure that neither modality is processed in isolation, which removes ambiguity. Note that the joint attention module doesn't come with its own parameters. The queries, keys, and values are computed separately by the two modality-specific encoders. The joint attention box simply computes and applies the attention scores. Finally, the joint attention output is bifurcated again. Image tokens flow to the left, text tokens to the right. They're each passed through their own linear output projections and continue to travel through the rest of their encoder. Even though the DiT and MMDiT were introduced in the context of image generation, they later became the basic building blocks for video generation models as well. But at this point, I'm tired, you're tired, and that's a story for another time.